used to teach very regularly, but again I have to go away sometime again next week at various times. So I will teach today, which is Tuesday, Wednesday, Friday, Thursday I won't teach, Monday, Tuesday of next week, then I'll be away for a week. So then after that I come back, we'll have to have some more lectures. Okay, so remember that for the last few classes, we've been thinking about how to model what is called DNA force extension or force extension curves. Remember that the prototype of the experiment is one where you take a DNA molecule, you attach it to some glass surface, let us say, you put a big bead at the end of it. The dimension of the bead is about 1 micron, so that it's big enough to be held and visualized in an optical trap. You mount the optical trap on a stage and can move it back and forward. Okay? So this helps to confine the bead. By moving the bead, you can measure what is the extension, delta x, let us say, of the DNA molecule. Finally, what you will do is to plot the extension as a fraction of the total length of the molecule, because you know the structure of the molecule, so you know what the total length is, as a function of the force. And typically this is done on a log scale here and a linear scale here. The curves that you get are something that might look a bit like that. Okay? The maximum value, suppose you say that the maximum extensibility of DNA is such that delta x divided by L has to be less than or equal to 1. So this is 1 over here, and this is what the experimental data actually look like. So I think I will probably give you a handout with the shape of this curve better illustrated. All you need to remember is that this is F, typically in piconewtons, and this is delta x by L, which is dimensionless. And what we wanted to do was try and understand the mechanics of DNA by trying to interpret the meaning of these force extension curves. So there were a couple of ways in which we began to think about this problem. One was to think about this just as a simple, let us say, Gaussian polymer. So start with the idea that DNA is just a polymeric molecule. So it's just some long molecule like this. And the extension is there is some preferred value of the end-to-end distance. By pushing this end-to-end distance a little further, you can ask what is the relationship between the force required to maintain a fixed distance between the ends. So imagine that this is one end and this is the other end, and you want to fix that distance and ask what is the force that is required to maintain it. So remember how we started thinking about this problem. We began with thinking about diffusion, and we said that if I took a diffusing particle, started off here at t equal to 0, landed up somewhere else at some different time t, and I asked what is the end-to-end distance r between the beginning point and the ending point. We found that the probability distribution of being at some distance r at time t, given that you started at the origin at time 0, was exponential of minus r squared mod r squared divided by 4 dt, and over here I had a factor of 4 pi dt to the power 3 by 2 in 3 dimensions. Okay? We wanted to relate, the way we began relating the diffusion problem to the polymer problem was to say that, look, you can think about this as well, equally well, as a shape or trajectory of a polymer with n steps. So for the polymer problem, we had some simple argument that started off with a lattice, and then we essentially took steps like this, and then we calculated r squared average, and we found that this was n times L squared, okay, where L was a basic unit here, and this also survived in a more general sense. If L was the sort of basic small step size, which was much smaller than any other length in the problem. Now from here, we know that this implies that r squared is twice the dimension, the diffusion constant, times the time. Okay? So now we said, let us relate this result here to this result here. In particular, we can take t as can take n to be something like T divided by L, the basic unit of the size. So let us look at these two things together and let us try and see how we would relate them. Just look at the notes for a second. Okay, so let us say that 2d dt, which is r squared for the diffusion problem, must equal n L squared, which is a result from the polymer problem. We want to try and understand what these combinations can be worked out to be. So this means that 4 times d times t, which is what enters here, is just twice n L squared divided by d. By just working that out here. Now we can take this result and put it back, because now we have everything that we need here. So what we get is, for the polymer problem, the probability that the polymer end-to-end distance r for n steps here is just, first of all, this factor, the exponential factor, which is exponential of minus. Now this factor comes up on top. So d is 3, 2 is 2 over here. We will put that factor back in here. So wherever we see 4 dt, we will put in the factor of 2 n L squared divided by t. So that will be exponential of minus 3 divided by 2 r squared divided by n L squared. Is that correct? The relationship that I wrote down over there? Divided by the factor of pi times 4 dt, which is pi into 2 by 3 n times L squared, whole raised to the power 3 by 2, which I can finally write as 3 divided by 2 pi n L squared to the power 3 by 2 exponential of minus 3 by 2 mod of r squared divided by n L squared. So that's now, I have simply mapped what we did, a lot of hard work in deriving this particular result for the diffusion case. Now all of those results now begin to pay off, because it's very easy for us to translate from one into the other. So this says that the probability distribution for an n step, for a polymer with n monomeric units here, so this is the polymer made up of n units, each with length L over here, as a function of the end-to-end distance, is just given by this particular relationship. Okay, I can make a few more changes here. First of all, the probability distribution of R, I can write the P n of R, I can write as being proportional to the exponential of minus beta times the free energy of having the two n's at R. Okay, this was motivated by our old results from statistical mechanics, where we said we related partition functions to free energies. And here, all we need to remember is the probability distributions of R are related to exponential of minus beta times some energy. In this case, I will call it a free energy, because it involves integrating out along the contour of the different polymer. Once I have this result, I have minus beta f of R, the free energy of a polymer with end-to-end distance R. This equals minus 3 divided by 2 R squared divided by n L squared. That's just this factor here. You may worry why I didn't worry about this factor. The reason is I can always write this as, first of all, that factor, e to the power minus 3 by 2 mod R squared by n L squared into e to the power log of this factor here, 3 divided by 2 pi n L squared whole raised to the power 3 by 2. Because exponential of log is just that factor itself. But now notice that the dependence, whenever you have things inside a log, so log 1 over n, that dependence tends to be very weak typically. So the strong dependencies are contained in this particular relationship. All these are contribute to what you might call logarithmic corrections to this basic result. So once n gets large enough, they don't really matter anymore. It's this object that really dominates. So once I understand that, I can write minus beta f of R as this, just relating this object to this object here, which implies that the free energy associated with the polymer with an end-to-end separation R is just kBt, factor of 3 divided by 2 n L squared times R squared. Okay, so that's our basic result, that the free energy is quadratic as a function of r, of the end-to-end distance. So from here I can say the force required to maintain, the average force required to maintain the end-to-end distance r must be delta by delta r of f of r from our old thermodynamic results. So if I do that, this becomes, I pull the factor of 2 down, this implies that the average value of the force that is required is thrice kBt divided by n times L squared times r. And that's our important result, because that relates the end-to-end distance, the separation, the extension, to the force required to produce that. Remember, we spent a little time on discussing where this came from. We said that, look, the fact that kBt is here is very important, because as t goes to 0, there is no force at all for a particular extension, which means that the only way this can come is from entropy itself, from the number of configurations. So this is called entropic elasticity, as I emphasized earlier. Okay, important point to remember over there. All right, so what this is saying is that if I plot f here, and r I can normalize divided by the extension here. It doesn't matter how I define that particular object here. So for example, I can say n times L is the total maximum length, capital L. So I can pull that factor in and I get average f equal to thrice kBt divided by n times r divided by L. But r divided by L is the analog of this quantity here, the delta x. So therefore, what this predicts is this relationship here is basically just goes like a straight line. And the slope of that straight line is proportional to this quantity here. So here I have the force, here I have the extension r divided by L, which is really the same as x divided by L, because the displacement in the direction of the force. All right. So now we have one result here, and we said that, look, if you think about DNA as just a simple Gaussian polymer, then the result must always hold true. So if I try to plot it on this line here, that line would actually look like something that would go off in that direction. It's correct here, but it gets very, very wrong as you move further out. All right, so then we try to improve this by something called the freely jointed chain. In the freely jointed chain, we think of a polymer as made up of a bunch of units. Each of them have dimension L. And I imagine that there is some force that is pushing on this in this particular direction. I can choose this to be the z direction, just because I can choose my coordinates to be anything that is really convenient to me. So what determines the energy of the system, assuming that all of these are independent of each other, these are all fixed size vectors, is exactly what angle this makes with the direction of the force. So let me write down an expression for that energy. This energy is the minus sign, the value of the force, the size of each step, times cosine of theta of I. So this is the energy associated with the ith bond in this chain. Look at this carefully. This says that when theta is 0, when theta is aligned completely with the force, which means a completely straight polymer here, this is the force, that means that this quantity theta, cos theta is 1 minus cos theta minus SL. This is the smallest it can ever be. Okay? Any deviation away from this reduces cos theta, takes cos theta away from 1 and increases the energy. So here is one way of saying that, look, if I think of this as made up of little units, little vectors here, let me call this vector T1, vector T2, vector T3, etc., all of size, the bond size L, each of them are independent in the sense they're freely jointed. There's no energy for this bond that connects them. Each of them is free to rotate around this particular point to align with the force here. Then writing down an energy that represents the alignment with the external force direction F. This F and this L is here in order to make sure that everything is dimensionlessly correct, because the force times the distance is an energy. and the cosine of course has no dimension at all. So here we have managed to write down the energy as a sum over independent energies. So the total energy for the full chain, E, is just a sum over independent energies, EI, where EI is the energy for each one of these bonds independently, because they're freely jointed. They can each rotate independent of each other. So then, again to remind you, we started off by evaluating the partition function Z, which was an integral over all configurations of all, let us say there are n spins. This is the orientation of each of those n spins, exponential of minus beta times the energy of each spin as a function of its orientation, the sum over I. It's exactly what we're supposed to do when we calculate a partition function. Now notice that each of these sums is independent of each other. It only involves an angle theta. So the way one would do this would be to write this as an integral for, say, d phi I sine theta d theta I times the factor of L squared. So this is imagining that each of these individual vectors can lie anywhere on a sphere of length L. So this is the right measure. So each of these distances here are specified by what is the angle theta that it makes with respect to the x-axis, and what is the phi that it makes with respect to its projection on the xy axis. So theta is with respect to the z direction here, and xy is with respect to the xy plane. The phi is with respect to the xy plane. Okay? So because each of these integrals are independent, this particular term reduces to just one integral, which is factor of 2 pi coming from the integral over d phi, and L squared coming from the measure factor here, because that's where it stops. Then an integral between 0 to pi of sine theta d theta times an exponential of beta f L cos theta, and then I must take this whole term and raise it to the power n. Is that clear what I did? I'm going a bit fast because you've technically seen all this earlier. I'm just redoing it a little bit. All that's important here is that each of these angles are independent. Each of these are vectors. This is one vector, let us call it T1. So another vector, call it T2. I can specify the direction of a vector completely by saying how big it is, and its magnitude is L. I also specify it by saying what direction does it point in, and for that I use spherical polar coordinates, where with respect to the z direction, it makes an angle theta. Theta can vary between 0 and pi. In addition, I take the projection of this on the xy plane, and I measure the angle that that projection makes, and that angle I call phi. Phi can vary between 0 and 2 pi because it's any angle in 2 dimensions. So phi changes between 0 and 2 pi, theta changes between 0 and pi, and the distance of this bond is fixed. So it's like a vector at a fixed distance. It's a fixed magnitude vector. So that's where all these factors come in, the factor of L squared. The factor of 2 pi comes from the integral over d phi. The sine theta d theta comes from the measure of this term. When I integral over dt hat, I must put in a factor. When I convert this factor into spherical polar coordinates, I have a factor that looks like this, times the energy which depends only upon the cos theta. Then remember that we did this integral. It was easy to do. We just said let us define a new variable x, which is cos theta. And then we made this integral between minus 1 and 1. We did the integral carefully. And what we found out was the final partition function was 4 pi sine hyperbolic beta times f times L divided by beta times f times L to the power n. That just comes from doing this particular integral, which we did the last time. We changed variables. Remember that we wrote the sine theta as d of cos theta with a minus sign. The minus sign enabled us to change these limits appropriately to -1 and +1. Then this becomes the simple integral dx e to the power something a times x, which is 1 by a e to the power a times x between the limits. Those two limits gave us a sine hyperbolic. The 1 by a gives us this factor. The 4 pi comes from this 2 pi times the 2 that comes from the sine hyperbolic. That's the logic behind this construction of this particular answer. Well, once we have the partition function z, z is a function of f, and the Gibbs free energy G of f is minus kBt times log of z of f. Remember, we have gone over these results of how you can take a partition function and convert it to a free energy. Once we take the partition function and convert it to a free energy, then now we can do interesting things with it. And one interesting thing we can do is to take the derivative with respect to that free energy. So R averaged is obtained by taking delta Gf by delta f with a minus sign. Okay? It's a response of the system to a particular force that we can actually calculate. So again, let me write down that result. R average computed from here is just n times L times cotangent hyperbolic f L by kBt minus kBt divided by f times L. That's the result that we had. Now, we can look at it for very small argument and for very large argument. For very small argument, the cotangent hyperbolic function, so cotangent hyperbolic of an argument x is 1 over x plus x divided by 3. The 1 over x gets rid of this factor. When I put it back in, the 1 over x gets rid of this factor here. The next factor is the factor of x divided by 3. Okay? So this is for small x. So R averaged must then be n times L times divided by 3 times, where did I lose those factors, over kBt times f. Okay? Which means that the relationship between f and r, so f is thrice kBt divided by, and there should be a factor there, by n L squared, which is the same result times r, which is the same result that I had here. Okay? So this is again goes back to saying that if this argument is small, which means the force is very small, then effectively it's as though it doesn't see the force at all except very, very weakly. So it's still in a sort of limit where it can point anywhere it likes with very small energy cost, which is more like the Gaussian polymer case, which means that again here that answer starts off exactly as the answer for the original Gaussian polymer. But the question is, does it do it all the way through? Because this is certainly now a more complicated function than the earlier function, which said it just remained straight and kept going up. For that, we need to look at the large force behavior of this function. When we look at that, that's easy to do, because all that requires is that we know what is the large argument of cotangent hyperbolic. Cotangent hyperbolic is 1 by tangent hyperbolic, and tangent hyperbolic for large arguments always goes to 1. Okay? So this answer becomes very straightforwardly R averaged is n times L into 1 minus kBt divided by f times L. Okay? So now here you can see that however large I make my force, this becomes smaller and smaller and smaller. So at infinite force, R is n times L. It cannot grow bigger than that. And the way it goes to that is through this 1 over f type of behavior. So it starts off the same as this Gaussian polymer case, but over here it behaves somewhat differently. And then it sort of behaves like that. Okay. So now we have looked at the Gaussian polymer case. Over here we have looked at the freely jointed chain case, but that's still not what the data is doing. The data is doing something different. So let us think a little bit about what it is doing. First of all, notice that this curve always lies above these two other curves that I have drawn, which means there must be some other source of energy. This says that for the same force, the extension is smaller in the experiments than it is predicted to be by either of these two theories of polymers. Okay. So now the question is, what is this additional source of energy that we have left out? Why is it that both these theories, one which doesn't assume any energy at all, it just assumes entropy, which is always correct here. The second one, which assumes that these independent parts that make up the polymer essentially move independently of each other. The chain is freely jointed. Even that, while it gets this part of the behavior right, the saturation of the displacement for large forces, it doesn't get the intermediate force behavior right. So there must be, as I said, some source of energy, some sort of source of other energetics that is not included. And the answer is that that comes from the fact that the freely jointed chain assumes that these joints cost no energy. Okay? That this is free to rotate, this is free to rotate, it doesn't matter at all. All that matters is how well this is oriented along the force direction, which is in the z hat direction. But accounting for how difficult it is to change this gives us a contribution to the energetics of the polymer that is proportional to the curvature of the polymer. And this contribution is called semi-flexibility. And this is an important term because you will see this a lot of the time in the biophysics of long chain molecules. Semi-flexibility is a cost for bending a chain. So let me write that down here. Semi-flexibility is an energy cost for bending the molecule or inducing some curvature in that molecule. And that comes from these junctions essentially. Because it says it's not freely jointed anymore, but you must account for the energy that is required for this to deviate from this direction. So how do we do that? Before we do that, it might be useful to just think a little bit about how one tries to qualitatively describe the different contributions to the energetics of a molecule like this. So to do that, for sort of instead of looking at a molecule like this, let's look at a slightly different but related model, which is just takes this and draws it as a sort of cylinder. And then asks, what are the deformations of the cylinder that are related to the description of the energetics of this molecule? Okay? There are a couple of things that you can do to a cylinder like this. One is you can stretch it. That is to say, here is your cylinder here. I can take it and pull at this end so that it now moves out a further distance, delta L. So suppose this equilibrium size was L, the increase in size is delta L. What is conventionally referred to as a strain is just delta L divided by L, the extension divided by the free unperturbed size. So that's one thing that you can do. You can stretch this without doing anything else. The second thing that you can do is to bend it. So you can take something that was initially straight and stiff like that with some central line, let me say drawn like this, and you can convert it to something that looks like this. And this deformation also costs energy of some form. That energy is proportional to, let us say, this distance r. Or if I try to bend it such that it actually looks like a circle, bend it into the form of a circle, how much I bend it is proportional to what is the radius of the sort of sphere that I can draw that includes that. The smaller the radius, the larger the energy, because the more tightly it is bent. The larger the radius, if the radius was infinite, it would just be a completely flat, unperturbed thing. So the energy must be proportional to this radius. It should not be proportional to whether I bend it upward like this or downward like this. These have different curvatures. So the energy is, at least to the lowest level of description, proportional to this radius squared. Because it does not depend upon whether I do it like this or I do it like this. The third thing that I can do is something called twist. And for twist, just imagine that I draw somewhere inside here a vector that consistently points in one direction in the unperturbed case. Twisting this corresponds to taking a situation where it is pointing upward in this case, but right at this end it points at some other direction. This corresponds to what we normally think of in twisting. If you imagine a perfect cylinder here, I take the end and I move it like this. That says that instead of this vector, if I sort of drew a vector like this all along, by moving this vector around on the surface, I have twisted this column. So the amount of twist is basically how much I have moved this. Let us call it some angle phi. So stretching, bending and twisting are three operations that I can actually do to a molecule when I think of it in a slightly macroscopic manner. And the way I will quantify it is, particularly for stretching, is through this quantity delta L by L. Okay. Let us introduce a little more terminology here. And the way we will do that is to try and imagine what is the sort of behavior that can give rise to a stretch. And one way of doing that is just to think of a bunch of springs connecting particles here. And let us imagine that in equilibrium, the separation is some A naught. Okay? Now I pull at it at this end. So now all of these things have changed their position, and this separation here has changed into A naught plus delta A. Okay. Because I have stretched it, I have to put in energy in order to do that, and I have now pulled this along to A naught times delta A, to A naught plus delta A. So the amount by which this bond size has increased is delta A. Okay. So now, let us now try and attack this in two ways. First of all, the total change in length delta L is just the number of springs times delta A, n times delta A. Okay. The number of springs is, of course, the total length divided by the unperturbed A naught. Okay. That's the total length is just n times A naught is just the total length times delta A. It's here. It's again just definitions. Now what we want to do is we want to say that I'm going to think of this material here as being made up of many of these strings of springs here. And there's a roughly constant density of each of these. So this is my way of thinking about a particular material. So if I take the area A, the cross-sectional area of this A, let me call this A, I divide it by A naught squared. This is the number of separate springs in parallel. Because all of these are now independent of each other. Each of these springs has some area which is A naught squared. Imagine breaking this up into lots of little boxes here. Each of them are separated by some distance A naught. And totally the total area divided by A naught squared is just the number of springs in parallel. If I have a whole bunch of parallel springs, then the spring constant let us say for m springs in parallel. So I imagine a situation where I have spring, 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 spring here, and I try and apply a force on that. The spring constant for a single spring k has now to be replaced by m times k, where m is the number of springs. Because springs in parallel, it's harder to move. Just sort of think of how you would do it physically. If they were all attached in series one after the other, it's equally easy to pull at it. But to put them in parallel, you have to fight against all of them together. So the spring constant now becomes much larger. It becomes a factor of m times k. And in this case, we know now the number of springs in parallel. This is, so we replace k by a divided by a naught squared times k. Okay? So now, the force that you apply leads to k spring constant here times a divided by a naught squared times delta a. This is the increase in length of the springs, which is k times a divided by a naught squared times a naught times delta L divided by L, which is k divided by a naught times the factor of a times the factor of delta L divided by L. Okay. Once I have that, I can rewrite that as the force per unit area is some quantity which I will call E into delta L divided by L. Where did I have small f? Capital F. I'm putting some force on it. Okay. This quantity here, a force per unit area, is sometimes called a stress. And we will see this later when we come and discuss continuous media, in the description of continuous media. This quantity E is called a Young's modulus. And this quantity here is called a strain. And this relationship here just says that stress, which is the force per unit area, is proportional to the strain. And the proportionality constant is in this particular case called a Young's modulus. Okay. This relationship between stress and strain is a more general one. It's particularly simple here because the geometry is very simple. It's just a simple cylinder which I'm just pulling into one here. I have an area here. I have a force that is normal to that area. But I can say, suppose I have a force that is not normal to that area, but at some tangential direction here. There is some component that might be normal, but there is some component that is also in this particular direction. How does that change the properties of the material on which I am pulling it at? It will turn out that that relationship then becomes a tensorial relationship between a stress and a strain. And a strain now will have two components. Stress will have two components. The stress will be replaced by some quantity called sigma ij, and the strain will be replaced by some other quantity called Eij, where there are two components here. This is a very simple description of just one of those components, just the diagonal components of the stress and the strain. But there's a more general description that relies on the fact that these are tensors and not simple scalar quantities, as we have written down so far. We will come to that maybe a little bit later and explain exactly what that means and how it can be understood. Okay. Now, I won't talk about the other parts of the, this is just to show you how a quantity such as the Young's modulus turns up. Yeah.
Strain is dimensionless, right?
Strain is dimensionless, yes.
And stress has some dimension.
Stress in this particular case has the dimensions of the Young's modulus, which is the force per unit area. let us now come back to our old calculation of trying to put in the bend energy, the bending energy, into the description of the molecule. So now what we had, remember, to start out with in the freely jointed chain was a set of vectors T1, T2, T3, T4, etc., 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 etc. And we said we wouldn't worry about the energy cost of having T1 next to T2, how much you bend between T1 and T2. We were just looking at each of these vectors independently as trying to align with some external force along some angle theta. But now we want to worry about this. So what is a model that we might use to represent the bending of this polymer? You want to assign minimum energy to the unbent configuration, which is a flat straight line configuration, and any fluctuation from that you want it to cost energy. One way to do that is to write the energy E as some J, sum over I, T I plus 1 minus Ti. And then I will put a square. What does this mean? First of all, notice I put a minus sign here, that the lowest energy comes when all the T's are the same. Okay? If Ti plus 1, if this says that if adjacent vectors, adjacent T's are all pointing in the same direction, then of course there is no energy cost at all to this particular. The moment I allow this Ti plus 1 to change from here, there's an energy cost that is proportional to how much the difference is between Ti plus 1 and Ti. Okay? So this is one way to actually write out this particular expression for the energy cost of the deformation, of this bending energy in terms of this quantity here. I've made one more approximation here, and that is to say that the size of each of these vectors, mod of Ti, is a constant. Because if it was not a constant, then I would have to add the energy of that to this. I would have to add an additional factor that says there's an other term responsible for the energy cost of how much this differs from 1. I'm just going to assume that there won't be any difference from 1. These are effectively fixed length units of the same size, and the only energy comes from a bending energy cost of that particular form. Okay? Sometimes it's also convenient to write a factor of 2, put that in there. Now this is not very convenient because it's a sum of vectors which interact with each other, and it's discrete sum over these. So it's a little bit messier than we might have wanted to be. So I'm just going to write down how one would conceptualize this model in the continuum, where I think of this as just some smooth vector like this, where at every point I have a local tangent vector t hat that tells me what is the direction in which it's pointing, where the energy cost comes when t hat at successive points deviates from the value at the previous point, so that the minimum energy is always a completely stretched pointing in the straight direction configuration. And then we want to see how to do that. So let's just do it in the following way. Let's just write this as minus j divided by 2, put in a factor of a squared here, a squared divided by a squared, sum over I, write this as ti I plus 1 minus ti squared, and write this sum. Okay? Now we want to take each of these a's, which is the size of each of these vectors, to be very small. When we do that, we can write this particular term here, t of I plus 1 minus ti divided by a, the whole squared, as d t hat by ds. Sorry. Yeah, okay, square and squared here. This is just taking something that is a discrete sum and making it continuous. Now I have to worry about these other factors that I have put in here. So let me just write those factors out. So that particular term I have is minus j divided by 2 a squared sum over I, and what I have here is d t hat by ds the whole squared, where s is some coordinate that tells me what is the distance along the particular chain. It's like it fulfills the same role that I did earlier. But now I can take this and write a squared sum over I is the same as a into a times sum over I. This quantity I can take to be an integral over ds. That implies that the total energy is minus j times a divided by 2 integral s varies from 0 to L d t hat of s by ds the whole squared times ds. And that is my most important relationship when I want to think about the energy of a semi-flexible polymer. Okay? Okay, I don't need a minus sign here. I can get rid of that minus sign really. I don't have a minus sign, I just have this particular term that appears here.
What is J?
J in the original term was the amount of, was an energy that reflected the bending. So if I bent this measured how much energy there was associated to that bend. So now when I write it in continuum form, I have J times the length scale here. And this is now my new quantity that I must worry about. This implies that minus beta times E is J over kBt times A times this integral 0 to L d t hat s by ds the whole squared times ds. Okay? This quantity here is dimensionless, factor of 1/2 here. So the length behavior is contained in this particular quantity here, in the A factor that I have here.
So why was I taking the whole square then ti plus 1 minus ti whole square?
Because we said that it didn't matter if it was like this or like this. It's only the dot product that mattered. It didn't matter whether I bent it like this or I bent it like this.
So to avoid the plus minus signs.
So I wouldn't have to worry about plus minus signs at all. All this is saying is that the moment Ti and T differs from Ti plus 1, there is a positive energy. So any deviation from a completely flat configuration, let us suppose this is I plus 1. So whether I went like this, whether I went like this, whether I went at any other angle, there's an energy cost for that. That only depends upon this particular dot product. So that's why this particular term appears here, and then is translated into that continuum form. Okay. This quantity here now has the dimensions of a length, and this is sometimes called the persistence length LP. So all of the behavior of this model is contained in the definition of a persistence length, which in terms of our original model is JA divided by KBT. Okay? All right? The only reason I'm doing this is just to emphasize what this LP means. And to do that, I will give you a result, but I won't tell you how it comes. And that result is, what happens if I look at the correlation of the tangent vector here with the tangent vector at some other point? So suppose I look at T of S dot T of S prime, and I can calculate this particular quantity here. How does this behave as a function of S and S prime? And the answer is that this behaves as exponential of minus mod S minus S prime divided by the persistence length. So the interpretation of that is that points that are close together tend to remain stiff. There is a strong correlation between, if S prime is very close to S, S and S prime are very strongly correlated. And they don't tend to deviate much from each other. As I make these points go further and further away, thermal fluctuations become more and more important. Beyond the length scale LP, as measured along the chain, they become so important that the correlation pretty much vanishes. It goes down exponentially. So the persistence length is a measure of how stiff the polymer is. The stiffer the polymer, the larger the persistence length. The more flexible the polymer, the smaller the persistence length. And that's what is contained in this particular description here. So the persistence length is a measure of how hard it is to bend the polymer. If I take a fluctuating polymer in at some temperature T, the persistence length determines over what length scale the correlation between the tangents goes to 0. Yeah.
How do you come to know that this dot product is a measure of e raised to?
So I'm not actually showing you how I get this result, because I would then have to do a little bit more work with how do I calculate averages. Remember that I can always do statistical mechanics given alpha minus beta E. What is difficult is to show you how to do the integral over all possible states, because now the integral over all possible states involves the integral over T's, over all the T's along this whole continuous curve. Because I'm not doing that, I just want to give you the final result and they concentrate on the features of the final result. And one important feature is that if I look at the correlation of how the tangents behave, at short distances, they behave as though they are very correlated. So some tangent here will continue to point in the tangent, the direction that this tangent is pointing. But at long distances, thermal fluctuations will always disorder it. And the length scale over which thermal fluctuations disorder it is the persistence length LP, which is why it is so important.
So does that mean the shape?
It has a meaning for the shape also. It means that over short distances it behaves like a rigid rod, which is hard to bend. Over long distances, thermal fluctuations become important, that it pretty much bends. It shows large fluctuations. The same sort of idea is when you take a stick and try and bend it. The shorter the stick, the harder it is to bend. The longer it is, the easier it is to make a bend inside it. And that's really a function of, it's not exactly the same, but it's related to the same intuition behind the persistence length. Okay, now having done this, having described the persistence length to you, I'm now going to quickly go through the calculation for the DNA molecule, putting in the bending energy. And we're going to do it approximately. We're not going to do the full calculation as it was originally, but let me just describe to you how that is done. So this is DNA. These models are called worm-like chain. They're otherwise known as WLC models. They're worm-like because a worm also doesn't have very large changes in the curvature. It tends to be a smooth object here, which is why the word worm-like chain is important in this particular context. So let's write down the energies. So beta times E is LP divided by 2 integral 0 to L ds d t hat by ds the whole square. That's the first term that we must have in our description, because that's a term that we actually derived explicitly. The second term is the energy of alignment. So this must be beta times the force times the dot product of each of these T's with the force direction. So that is, again, this must be an integral. So this integral comes over both of these terms here, and that's what it does. So the force points in the z direction. The force dotted with the t hat is what forces the t hat to lie in the direction of the force. That's why the minus sign also helps. And the factor of beta must be there because this is beta times the energy. Okay? So this particular term here just comes from semi-flexibility. And this term here is a term that represents alignment. alignment with the force. I use the notation T hat. Huh? I don't. We No, it's correct here. No, it follows the same. Follows the same thing. It's beta times E.
When the last time the minus beta is substituted, right?
That should have been beta times E. Okay, so now we're going to try and do this calculation, but we're going to make one very important simplification. We're going to assume that the force is large enough that the polymer is more or less straight in this direction. There are only small fluctuations about that. Okay, so the polymer trajectory I'm going to define as T hat at any S is mainly proportional to mainly pointing in the z hat direction, so z hat times T parallel, but there is some small component which is perpendicular to that, which I will call u, the vector u. Okay, so this is saying break up the T into a component that points in the z direction and a component perpendicular to that. The component that points in the z direction is T parallel. The component that points perpendicular to that is some vector u. Now this is a unit vector, so T hat dot T hat at the same S must be equal to 1, which means that z hat T parallel plus u dot z hat T parallel plus u must equal 1. Okay. Now because z hat and u are perpendicular to each other, this implies that T parallel squared plus u squared must equal 1. That further implies that T parallel must equal the square root of 1 minus u squared mod u squared to be strictly correct. And if u is small, because it's mainly pointing along, if T parallel is close to 1, this is mainly pointing in this direction. So u can be assumed to be small. This is 1 minus u squared divided by 2. Technically speaking, mod u squared divided by 2 and higher order terms. Okay? So T parallel is 1 minus mod u squared divided by 2. We can take this now and put it back into this particular expression here. Okay? And when we do that, what we find is from the first term beta times E is, first of all, there is a term which is 1 that I will neglect here. The second term is a term that looks like 1/2 integral 0 to L ds. The first term here is LP times du by ds the whole squared plus beta f mod u the whole square. All I've done is I've just taken this term here and evaluated this particular quantity here using that particular approximation for T parallel. Is that clear what was done? We are always working in a limit where we are almost straight in this direction. And I can make these important approximations for T parallel in terms of u and write everything in terms of u, which is really what I want to do. Once I have something like this where u appears explicitly here, remember that u is only quadratic. There's a quadratic term here and a squared term here. So I can use a Fourier transform. And when I use a Fourier transform, I choose it in the form u of q is integral 0 to L ds e to the pi q s u of s. Okay, technically this is a vector, I'm not writing the vector signs. U is actually a two-dimensional vector there. Now I can take this and put it back in here. When I do that, this derivative du by ds gives me a factor of q squared. This term here becomes beta f times us here. So the total energy beta times E will then become 1 by 2L sum over all Q LP Q squared plus beta times F of mod UQ squared. Just hold on for just one more minute, because then we're very close to getting the final result. Okay? Over here, notice that this is the form. Something here, sum over independent terms, quadratic term here. Okay? We've seen this before, because we described this briefly in our discussion of the equipartition theorem. It said that whenever you can write the energy as a sum over quadratic terms, each of those terms can be assigned an energy of kBT. Most important result. Okay. So that means that we can very simply just say, all right, the average value of UQ mod UQ squared, should put vectors here technically speaking here, mod UQ squared is 2L divided by LP Q squared plus beta times F. This is our main result up to this point. Okay? And similarly, U of S squared average is just a Fourier transform of this object here, which is twice integral minus infinity to infinity dq divided by 2 pi 1 over LP q squared plus beta times f, which I can actually evaluate. This becomes 1 over square root of beta times LP times f. There's a little bit of algebra here, but I don't want you to worry too much about it, because we are just one step away from the answer that we actually want to get. And I'll tell you what that answer is just now. The extension in the force direction is given by L T parallel is L into 1 minus 1 over square root of 4 beta LP times F. And let me write x over L minus 1 as minus 1 over square root of 4 beta LP times F, or 1 over x over L minus 1 squared 4 beta LP times f. This is just algebra that you will have to follow up when you go back and do it here. I just want to give you the final answer. So the final answer is, when you simplify it, you can write an interpolation formula that gives you the right behavior at small f as well. And that interpolation formula has the form f LP divided by kBt equal to 1 over 4 into 1 minus x by L the whole squared plus x divided by L minus 1 by 4. Okay? So first of all, check that for small x by L, the answer that you get is the same as the answer that you got for the Gaussian case. This is by construction. Even though this calculation was done in the large force regime, by construction you add these terms here to provide the right way of interpolating between one answer and the other. But what is interesting about this is the large force behavior. Yeah, just one sec. I'll just write down this final answer and then we can come to the question. So at large f, I have x approximately equal to L times 1 minus 1 divided by 4 beta f times LP. And this is the most important result. The reason is, remember the old result. The old result was 1 minus 1 by f something. Huh? Now it is 1 minus 1 by square root of f. Square root of f is a slower function than f. It goes down. So if you take this relationship, you take the interpolation formula that was actually first written by John Marco and Eric Sigia. If you take this formula that describes the relationship between the force F and the extension x, and you plot it against that data, what you get is a curve that pretty much fits precisely what that data looks like. Okay? So now we understand that the real way of thinking about DNA is to account for the flexibility of DNA. Not just the fact that DNA is a simple Gaussian molecule which can flex infinitely, but the fact that it is semi-flexible. It is flexible at large length scales, but at short length scales, bending energy matters. And that gives you the important correction that is required to take you from the freely jointed chain to the semi-flexible or worm-like chain. So now there's ample proof of the fact that for large x, this satisfies the square root of x type of behavior, square root of force type of behavior. And then this is actually such a successful formula, and this paper is probably cited more than 1,000 times or something like that, that now this theoretical formula is used to benchmark experimental data. That when you want to standardize an optical trap, you make a measurement of DNA in that optical trap and you pull at it. And then you see how well does it fit this particular formula. And all of this, remember, there's only one parameter in it, and that is this quantity LP. LP you can determine from some other measurements. And you can say that that is the LP that defines for me how flexible my chain is. I can take it, put it into this term, draw my data, plot my data, and then see how good this flat is. The better it is, especially at small forces, small extensions, the more accurate your description, more accurate your calibration of your trap also is. Yes, Kiran, you had a question.
So we wrote beta E in terms of dt by ds,
Hmm.
and then we did ds is equal to something plus something.
Yeah.
Then we wrote beta E is du by ds. So
Yeah.
what happens to the t parallel? Like the ts.
I got rid of one of those terms by imposing a condition. So remember that we said that it is t parallel, so t hat I wrote as t parallel times z hat plus a vector that is perpendicular to it. Then we said, oh, there's one more condition we have to apply, that is the modulus of t hat is 1. That means that this and this are not independent of each other. Because of that, I can write everything in terms of just the 2 hat and eliminate wherever t hat. Remember the relationship that we wrote down. We wrote down t parallel is square root of 1 minus u parallel squared, 1 minus u squared. That means wherever I had T parallel, I could replace it by the U. And that's essentially what we did to finally get something that was completely in energetics in terms of the U. I can only do this when the chain is sufficiently long, because only then does this approximation apply. Well, okay, so I can always do this, I can always do this and this, but the expansion of stopping the square root at just that particular term, at just the quadratic term, I can only do if the U is small. So there is some amount of calculation here which would be good if you could follow, but what I want you to remember, what I would like you to take away from this, most importantly, is the following. First of all, you should understand what semi-flexibility is. And semi-flexibility refers to the energy cost for bending. That is an important result. And all of you will come across the word semi-flexibility in many different contexts in biophysics. Semi-flexible polymer networks, semi-flexible polymers, etc., etc., semi-flexibility in membrane configurations, etc. It will turn up in many different places. So this is a reflection of the fact that curvature costs are important. The second thing is that it would be good if you could remember the Marco-Sigia formula, the main essentials of the fact that the way it differs from the earlier versions is the 1 minus 1 by square root of f type of behavior, which is what really makes the difference in comparison with the freely jointed chain, the Gaussian polymer, and the actual physical situation. Okay? The other things are not particularly important, so I won't stress them at this point. The rest of this is just calculation based on what you know already about semi-flexible polymers and so on. Or what you know already about the equipartition theorem is just an application of that. But the main thing is you must understand what semi-flexibility is, and maybe we'll discuss this a little bit later on. I referred briefly to the Young's modulus, the stress and the strain, Young's modulus, stress, strain. We will see these again in the future because they will be important when we think about continuous media. So the next time what I will do is probably describe a little bit about the physics of membranes, taking off from here and ask how does one best describe a membrane, and take any further questions that you might have about this particular description. But this is how we now understand the theory of the worm-like chain is now how we understand the mechanics of DNA in a simplified sense. There are many more complicated models, but in a sense this is the simplest and the most general description because it involves only one parameter, a persistence length, which you can determine independently. And it has a beautiful fit to data over something like 4 orders of magnitude in force. Okay? And there are many other experimental consequences of these which people are continuing to study. All right?